Hey everyone. In this video, we're going to look at how rigid motions can help us prove certain things in geometry. So in the diagram below, it's given that line AB and line CD intersect at E. The angle pairs across from each other in this diagram are known as vertical angles. So we've already talked about the vertical angles, so we're just going to state what they are in this case. So one pair would be angle AEC, and the other one would be angle DEB. So that's one pair. And the other pair would be other angles here, angle CEB and angle DEA. And notice with the blue arcs, I only put one, and the green arcs, there's two, because that's just an indication of which ones are congruent to each other. So remember, vertical angles are always congruent. Any pair of intersecting lines will form vertical angles. So angle AEC is congruent to angle DEB, and angle CEB is congruent to angle DEA. Now, although there are a few different rigid motions that would map angle BEC onto AED, remember that is just equivalent to our green arcs here. They're just written in the opposite order, and that's fine too. We will use 180-degree rotation of angle BEC about point E for our proof. Now, finish each statement with the reason. So there is a cheat sheet posted to Google Classroom. I'm not going to go back and forth to use it, but something that I would look through later. But if I'm going to start here, we're going to have that the line EB is rotated 180 degrees about point E, and it falls on AE. And when EC is rotated 180 degrees about point E, it falls on ED. So let's just look at that for 1 second here. Here's my line segment. Now, remember, when I'm looking at E, that point's not moving. So we know E is going to stay in there. That's what's known as our center of rotation. And we saw that a little bit today in our class lesson as well. But E is not moving, but I'm going to rotate 180 degrees around. So bear with me as I'm off a little bit. But if I go 180 degrees, that's my line segment. That's why it falls on AE. Similarly, if I had EC rotated 180 degrees around E, then it would fall on ED. Well, let's look at that. Now we're talking EC here. Same thing though, I'm trying not to move E at all. I'm rotating 180 degrees, so I'm going around to a straight line, right? Bear with me as my finger moved a little bit, but it would land on ED. The reason for this is because rotations, oops, let me put that in there, rotations of 180 degrees around a point on the line they extend the same line. Basically, what that means is anytime we try to do a rotation of 180 degrees, if your point, your center of rotation, is on that line, it's just making the line a little bit longer, which technically we know lines go on forever, so it's not even necessarily making it longer. It's just extending it further. Okay. So basically, when I think about that rotation, okay, let's say I extended it a little bit further to my angle here. If I look, oops, I'm gonna do that real quick. If I look at those two and I keep that angle in the same spot and I attempt to rotate 180 degrees, now bear with me, I'm trying to maintain that same, I slipped my finger a little bit, but notice that angle is preserved. That's why the angle BEC and angle AED, that's why they're congruent to one another. Okay, that's why we know that vertical angles are congruent. Okay, now let's go look at another reasoning with rigid motions here. In exercise 2, we have in the diagram below, it is given that the line AB and the line CD are parallel and cut by this transversal line M, which intersects AB and CD respectively at E and F. Now remember, order matters. AB came first, so that intersections at E on that line. CD comes second, and as well as F, and that's the point that gets intersected there. We also know that point H is the midpoint of segment EF. So we want to name both pairs of alternate interior angles. So it's our first time hearing these vocab terms, but keep in mind, alternate interior angles are exactly like what they sound. They're alternate sides of the transversal, but inside of the parallel lines. So here are my two parallel lines. They're cut by this transversal here, right? So when I'm thinking about this, I want to be inside that. So here's one of them. And so now inside, but on the alternate side of the transversal, there's one pair of alternate interior angles. So we would have angle DFH and angle AEH. Now, that's not the only way we could write that, right? We could kind of write further like AEG, a bunch of different ways, but we won't get too caught up on that right now. The other pair of alternate interior angles are going to be angle CFH and angle BEH. Now, parallel lines cut by transversal also create corresponding angles. One pair, now I'm sorry, that pair, for some reason spelled wrong, but one pair would be angle GFD and HEB. So if I look at what those are, GFD is here, HEB is here. So corresponding angles are on the same side of the transversal, but one's inside my parallel lines and the other's outside. So kind of think of a correspondent for those of you who like sports. Your correspondents, you have some that are on the field and back in the booth somewhere else. So when you're thinking of that, you have one inside the action and one outside the action. So that being said, my next pair would be maybe here and here. Now, it's hard to name these angles because right now I don't have anything on the bottom line of M. So what you can do in this case is you can always go in and label your picture. So I'm going to call this angle 1 and angle 2. So that is something else that we can do in geometry. The only thing though that to be able to label those is you have to make sure you label your picture. You can't just tell me angle 1 and angle 2 and not have that drawn in on the picture because I don't know what that would be then. Okay, so in that same fashion, we could keep going. Okay, and we could have the ones on the other side. Now, I could label these with letters, or I could call them 3 and 4. And finally, there'll be one more pair of angles for us, and I'll just call them 5 and 6. And what I'm about to show you, since I already set them up congruent to each other, is that they are all congruent. And to prove this idea, we're going to use translations. So we're going to show that FEB can be mapped onto GFD. So I'm going to erase everything that I have in here for a moment. Actually, let's keep that all there for a second. I'm just going to actually use a different color so we can see what I'm talking about. So I'm going to try to get a bright color that stands out. So we're starting with FEB here. So here's our angle FEB. All we want to do is translate. So we're going to translate by, just remember, it's just our sliding motion. We're translating EB in the direction of EF. So along that pattern, we're going up along that line such that E gets to point F. Then we'll see what happens. Oops. So I'm just sliding along here along the path of EF until E gets to F. Notice my angle is exactly the same by that translation. So anything to do here, we know that translations had a special property that only the translation has in a rigid motion. Translations create parallel lines to the original. Okay. And anytime we have parallel lines that are cut by a transversal, we're always going to form alternate interior angles. I'm just going to abbreviate that so it fits. And corresponding angles. Those are two angles that will always pop up when you have parallel lines cut by a transversal. Okay. And every pair of corresponding angles are congruent, just like every pair of alternate interior angles are congruent. Okay. Now, those alternate interior angles kind of build from what we saw with the vertical, but they would slide and then rotate. So they'd be a combination of vertical meets the translation. So rotations and translations get us the alternate interior angles to be congruent. So that being said, in exercise 3, we have a diagram to the right. Lines L, M, N, and P intersect at line R. Which statement must be true? So we're trying to figure out which pair of angles must be parallel to one another. Well, this is a multiple choice question, so we can kind of look and cheat a little bit to see which ones make the most sense. But if I'm looking at this picture, when I take that moment, I probably would want to start with the ones that kind of look the best. Now, I have to look at it, but I can't say that would be my reasoning. But what I can say is that angles on a straight line like this right here have to add up to 180. So I know that this angle would be 68 degrees. Well, if I look where the angle is here, we have one inside and one outside the parallel lines, but along the same side of this transversal. So those are corresponding angles. So line L would be parallel to line P. Okay. Continuing on, we do have an explanation question in this case. So we have the following diagram. We have line segment BEC and AED, where AD is perpendicular to DC, EB is equal to EA, and the measure of A is equal to 67 degrees. Now we want to justify why angle C must be 44 degrees. So having this explanation question, we want to just kind of make sure we're using words to write out everything that's important. So I'm going to start with EB equaling EA. Okay. And I'm also going to draw in angle A is 67 degrees. Well, one thing I should notice when I have two sides congruent like I do here, just going to make that a little bit nicer. Well, we should know that this is a specific type of triangle. That triangle, AEB, is isosceles. Okay, we know that because it's got two congruent sides. And we also talked about isosceles triangles having, if they have two congruent sides, they have to have congruent base angles. So angle A is going to be congruent to angle B because of that. So we already know that we have 67 degrees in that spot as well. From there, I know that this angle has to be whatever would add up to 180 degrees. So I could take a minute and just say 67 plus 67 equals 134. And then we have 180, subtract 134. So we're looking at 46 degrees. So angle BEA equals 46 degrees. because triangles equal 180 degrees. Notice I had to call that one BEA because I couldn't just call it angle E if there's one on each side of that angle spot. But now, following up with that, I also know DEC is 46 degrees because vertical angles are congruent. That's just another way to write angles with that little arc in there. And one last thing we know is we have perpendicular. So if AD meets DC, there's going to be my right angle. So remember, perpendicular lines form right angles. And then by our reasoning, we already know that triangles add to 180. So I've already written that down. But that means I would just add those two angles. 90 plus 46 is 136. When I subtract that from 180, we in fact get our 44 degrees, which is what we wanted to show. And so now that's my explanation of why that's true. And I've done all my steps along the way. Okay, again, you don't need perfect sentences or anything like that, but you do need to make sure you're stating the geometric properties that lead us there. Now, one other thing we're going to use to kind of explain here is show what other kind of things rigid motions can do. So in the following diagram, it is known that AB bisects both angle CAD and angle CBD. Given this information, we can map triangle ADB onto triangle ACB using rigid motions. And when we do that, we'll be able to prove that the triangles are congruent. Because remember, rigid motions prove our congruency as long as our original shape can be mapped onto the image, that new pair. So if we can make that happen, if we can use rigid motions to show that, it's enough to show the triangles would be congruent. So in this case, it says what angle pairs must be congruent? Well, AB is bisecting both of those angles. So we have angle CAB is going to be congruent to angle DAB. And we also have angle CBA congruent to angle DBA. Okay, the reason why is we know an angle bisector creates two congruent angles or cuts an angle in half, something along those lines. Now, there's two fixed points currently, and I can identify them pretty quickly. So if I'm mapping ADB onto ACB, notice when I stack those, there's two letters that are in the exact same spot already. Those are my fixed points. So because I have these two fixed points, I know that this transformation would have to be a reflection. Okay, remember, a reflection needs a line to reflect over. So a line has to at least have 2 points that would line up with one another. So it's because we have two fixed points that's going to lead us to our line of reflection, which in this case, the line of reflection would be AB, because those are the 2 points that are fixed. Now, our non-fixed point would be mapped from D onto C. Because remember, it tells me the direction here, ABD onto ACB. So D would go on to C. And if we want to explain why these triangles are congruent, well, think about what a reflection is. The whole point of this whole unit, what we keep referring back to, is our rigid motions. And we know rigid motions, like a reflection, preserve length and angle measure. So that's just one way of getting our rigid motions to map onto one another. We could have any of the types of rigid motions, like a reflection, a translation, or a rotation, or we could have a combination of them. But for here, one final example we have, in this case, we have the following diagram is known that we have line segment ACD, BCE, with C being the midpoint of both AD and BE. So because it's the midpoint of both, that means AC is congruent to CD and BC is congruent to CE. Given this information, if we can map the triangles onto each other, it's enough to prove that they're congruent. Now, we don't have two fixed points this time, because if I look here, we have triangle ABC and we have triangle DEC. I only have one fixed point. I only have C and C that match up. So if you have one point, that's going to need something that has only one point involved. That's going to be a rotation, because remember, there's always a point that it's going to rotate around. When we were doing it on the Cartesian plane, the coordinates, that was the origin for the most part, right? So if you have one point that they overlap, we're going to do a rotation. But we're going to be specific. We're going to rotate about C. And I could say 180 degrees in this case because I know it's a straight line, but we could just say mapping one of your other points onto each other. Now, in this case, they weren't specific in the directions of which triangle mapped onto, so you can decide. But I just picked one of my other points. I'm going to say mapping A onto D. You could have also said B onto E. You could have done D onto A or E onto B. Oh, E onto B, excuse me. Any way would work in this case because there was no specific instruction of which way to go. But we want to make sure we're clear about that mapping. I could have also done rotation about C 180 degrees because I saw a straight line, but sometimes the picture won't make a beautiful like line like we have here. So we can always kind of avoid that by just writing mapping one of those points onto each other. Because if I do that, the other points will follow suit and all fall on there. Because if I just want to take a quick peek of what that would look like, let's say here, if I highlight our triangle. Now, I'm going to keep my finger now. Bear with me. I'm trying to keep it. I'm rotating 180 degrees around this point. Notice I'm good. But I started at C and I mapped A, or I could do A onto D. In this case, I did D onto A. But if I went back again and just kind of rotated it back, A until, move my finger, until it gets to D. But notice that's just the case there. Okay, guys, we're going to do a bunch of practice with kind of combining them tomorrow in class. So we'll regroup there, but thanks for watching.